Today we're going to design a TinyURL system. The kind of system design problem that shows up frequently in FAANG interviews. We'll walk through the requirements, scale, architecture, APIs, and trade-offs, exactly how you would explain this in a real interview. Problem with long URLs. Let's start with the problem. Long URLs are hard to share, hard to remember, and they often break in messages or social platforms. A URL shortener solves this problem by converting a long URL into compact, easy to share link that redirects back to the original destination. From a functional perspective, the system needs to support two core operations. First, creating a short URL using a PostView API. Second, redirecting users from a short URL back to the original long URL using a GET request. Everything else we add later on is an optimization or an enhancement. Let's define our non-functional requirement. We'll design the system to handle 1000 requests per second, maintain low latency under 100 milliseconds, and provide high availability greater than 99.99%. These requirements will drive most of our architectural decisions. Before jumping into architecture, we need to understand the scale. At 1000 requests per second, we are handling roughly 86 million requests per day, about 31.5 billion requests per year, and roughly 315 billion URLs over 10 years. Assuming each URL record is about 100 bytes, that's around 30 terabytes of storage over 10 years, which is very manageable using modern distributed databases. Next, we need a way to generate a short unique keys. We generate a numeric ID either via auto increment or distributed generator and encode it using base 62. Base 62 uses digit lowercase letters and uppercase letters, giving us 62 possible characters. With just 6 characters, we could get nearly 57 billion combinations. And with 7 characters, we get over 3.5 trillion, which gives us comfortable long-term headroom. Base 62 is compact, URL safe, and human friendly, making it a great fit here. Now let's look at the high level architecture for creating a short URL. Technology choice. We use Redis in front because this is a read heavy workload and we want sub-millisecond lookups for hot URLs. Cassandra is used as the primary data store because it scales horizontally, handles high write throughput, and gives predictable low latency at scale. Each choice here is driven by access patterns and scale, not by preference. The client sends a request to a load balancer, which routes it to one of many stateless web servers. The service generates a short key, stores the mapping in Cassandra, and then writes the URL into Redis cache for fast feature access. Configuration data is managed using a system like Zookeeper or any dynamic configuration service. For redirection, the flow is even faster. The client hits the load balancer, which routes the request to a web server. The server first checks Redis cache. If the URL is found, we immediately redirect the user. On a cache miss, we fetch from Cassandra, populate the cache, and then redirect. This cache aside pattern ensures low latency for read-heavy traffic. Here's what the post API looks like. The client provides a long URL, an optional TTL, a custom alias if desired, and a user ID. On success, we return 201 created response. We also handle validation errors, duplicate aliases, and rate limiting at the API layer. Get API design. The get API is simple. The client requests the short URL and the service responds with 302 redirect, pointing to the original long URL. Redirecting instead of proxying keeps the latency low and minimizes backend load. Schema design. This is our core data model. We store short key as the primary key along with the long URL, user information, timestamp, expiration, and analytic fields like clock count. The schema is optimized for fast hookups by short key, which is most common access pattern. Finally, there are several important follow-ups. We add security controls to prevent malicious users, rate limiting to control against abuse, and analytics to track usage patterns and user behavior. And thus a complete tiny URL system design from requirements to scale.